So in this video, I will review the properties of exponents with you. I'm actually going to skip to the second half of the worksheet since that starts with the rules, and I'm going to go through some examples applying those rules. So the first rule of exponents is the product rule. And then following from that is the quotient rule. For these two rules, you must have equal bases for them to work. So an exponential function consists of a base b raised to a power u. So I want my bases, my b values, I want them to be the same. So when you have two exponential functions being multiplied and you have equivalent bases, then the result is b to the power of u plus v. You simply add the exponents there, keeping the base the same. For the quotient rule, it's the same thing, but with subtraction. So the b to the u divided by b to the v, you get b to the power of u minus v. So again, you need equal bases to use those two rules. They will not work otherwise. The next three rules are kind of related in their own way, where you have different ways to distribute exponents. So the power of a power rule, 5b to the u, and then that exponential is raised to another exponent v. What you must do there is multiply the exponents. So you get b to the power of u times v. The power of a product rule, and you have a product raised to a power, you may distribute the exponent to both terms. So you get a to the u times b to the u. So that when you have a product raised to a power, you can distribute the exponent. However, in the case of, let's say, 3 plus x squared, where it's a sum or a difference raised to a power, this is not equal to 9 plus x squared. To correctly multiply this out, you would need to use the box method. And you would see that it's not only 9 plus x squared, but also plus 6x that's in there as well. So you can safely distribute an exponent over multiplication, not addition or subtraction. You can also distribute the exponent over division, which is the power of a quotient rule. Because division can be interpreted as multiplication, like a over b is like a times 1 over b. So you may distribute the exponent over multiplication or division. The result of this, you get a to the u over b to the u. And then the last few rules, the zero exponent rule, b to the 0 power is equal to 1. So any number to the 0 power is 1. Negative exponents mean you take the reciprocal. 1 over b to the u is the result of that. So really that negative exponent rule, it takes, when you have a negative exponent, you take the exponential term and you move it to the opposite part of the fraction. So for example, if I have 1 over 2 to the negative 2 power, this negative exponent means you bump it up to the other part of the fraction. So you get 2 to the positive 2. And then that would just equal 4 from there. And then fractional exponents can be interpreted as taking the radical of a number. So v in that fraction is the index of the root. So this is really the vth root of b to the u power. The numerator is the exponent of b. So let's do these practice problems together, applying these rules. For 1a, we have a product 8x raised to the power 4. So we're going to use the power of a product rule for number 1a. This is 8 to the 4th times x to the 4th. 8 to the 4th is 4,096. And then times x to the 4th, that is your answer. For 1b, we have a complicated fraction. When you have a fraction with all these exponential expressions going on, you're not sure where to start simplifying. Well, most of the time, you can just pick one part to start with and then deal with the other part later. So I'm going to take care of the numerator first, and then I'll deal with that denominator. So in the numerator, I have 4 cubed, and then that entire thing is being squared. So I have a power to a power. Hence, I use the power to a power rule, where I multiply the exponents. So 4 cubed squared is really 4 to the 6. And then it looks like that's all I can do to the numerator for right now. For the denominator, I have 4 to the 4th power times x to the 0. So x to the 0 is just going to be 1. That's the 0 exponent rule. And so I really just have 4 to the 4th times 1. I'll just write 4 to the 4th. So now I still have a fraction. I have equivalent bases. I got 4 and 4 as my bases. I can use the quotient rule, where I subtract the exponents. 4 to the power of 6 minus 4, I will get 4 squared, and that's 16. So 16 is my answer. So it's a very careful approach to simplifying these complex fractions. Just take one piece at a time. For 1c, I got 27 to the negative 1/3 power. So it looks like this is combining the negative exponent rule as well as the fractional exponent rule. Well, I have a negative exponent, so I should probably deal with that first. So by the negative exponent rule, the result is 1. And then you rewrite the original expression, but now with a positive 1/3 exponent. And then 27 to the 1/3 power, that really means you're taking the cube root of a number. So I want the cube root of 27. 27 happens to be a perfect cube. It's 3 to the 3rd power. So we get 1/3. All right, number 2, some more expressions here. These ones consist exclusively of variables. So for 2a, I got 3 times the quantity d to the 6th power, and then that term is raised to the 4th power. So notice that 3 is not being raised to the 4th power. It's only d to the 6 being raised to the 4th power. The power to a power rule is where we multiply the exponents. So I get 3 times d to the 12th. And that's really all I can do here. Or not 12. 6 times 4 is not 12. It's 24. That's all I can do there. I can't simplify further. For part B, I have another complex looking fraction. So I'm going to take it one step at a time. I'm going to start with the numerator first. I notice that I have the 7th root of g cubed. So if we write that as a fractional exponent, the 3 is the numerator of the in the exponent, and the 7, that index, is that denominator. And then times g to the 7th divided by g to the negative 1. It's easier to deal with fractional exponents as opposed to radicals when you simplify. So that's why I did that step. And now in the numerator, I'm multiplying 2 exponential expressions of the same base. So that means I get to use the product rule, where I add the exponents since the bases are equal. So I got to do 3/7 plus 7. So on the side here, 3/7 plus 7. I need a common denominator. 7 can be rewritten as 49/7. And then I do 3 plus 49 to get 52 over 7. So now I have g to the 52/7 power, all of that over g to the negative 1 power. Okay, the numerator looks pretty good. The denominator, we have a negative exponent. So that means g to negative 1 will be pushed back up to the numerator, and we turn the exponent into positive 1. So I have g to the 52/7 power times g to the positive 1 power. And then, again, I have equal bases, meaning I can add the exponents here. So I'm multiplying the 2 expressions. 52/7 plus 1. 1 is 7/7. So this is g to the power of 52/7 plus 7/7. The result is g to the 59/7 power. That's as far as we can go. Or you may write it as the 7th root of g to the 59th power if you feel like doing it that way. Our last problem, m to the 2/3 over n to the 3/2, all of that raised to the -6 power. So there are a few ways you could approach this, but I think the best way is to immediately distribute this exponent. This is the power of a quotient rule that we're using first. Remember, you can distribute the exponent over multiplication or division, but not over addition or subtraction. So I gotta multiply these exponents by -6 because I'm also going to use the power to a power rule at the same time. So 2/3 times -6 is -4. And then 3/2 times -6 is -9. So now I still have a fraction. Both parts have exponentials with negative exponents. You can just swap their positions pretty much. Since m to the -9 will move to the top and become m to the +9, m to the -4 will move to the bottom and become m to the +4 power. And then by the quotient rule, this is m to the power of 9 minus 4, which is m to the 5th. And so those were properties of exponents and some examples applying them. I hope you found this helpful. Have a great day. Go Riders.